our first speaker, Professor Svetlana Zhilina from Moscow State University. The title of talk, the divisor graph of real Cayley-Dickson algebras.
Thank you very much. I'm not Professor Svetlana Zhilina, I'm just Miss Svetlana Zhilina. I just graduated my specialist program from my specialist program, so I'm just a student. So the topic of my talk is zero divisor graphs of real Cayley-Dickson algebras. I will explain all words in the title. And this joint work with my scientific advisor, Professor Alexander Guterman. Okay, first of all, I will recall the definition of real Cayley-Dickson algebras. Cayley-Dickson algebras occurred yesterday in the talk of Adam Chapman. You have already seen this definition. Let A be an algebra over a field F with an involution. A can be non-commutative, non-associative, or even non-unitive. We take a non-zero field parameter gamma. Then the algebra A gamma produced by the Cayley-Dickson process is defined as follows. Its set is the set of ordered pairs of elements of A with component-wise addition, standard addition, and multiplication and involution are given by these two formulae. Note that gamma occurs only once in the formula of multiplication. If the algebra A is unital and the involution on A is irregular, that is, for any element we can define the trace and the norm as follows, and they belong to the field. Then the evolution on the new algebra is also regular. And for any element, we have the following relation. Its trace coincides with the trace of its first component, and the norm depends on gamma. Okay. We'll consider only real Cayley-Dickson algebras, so we now assume that our field is a field of real numbers. So let n be an arbitrary non-negative integer. And gamma 0 and so on, gamma n minus 1 be non-zero real parameters. Then we define a real Cayley-Dickson algebra an as follows. We first take the field of real numbers as the algebra of itself, and then apply the Cayley-Dickson construction n times. First with gamma 0, then with gamma 1, and so on, and the last one with gamma n minus 1. Clearly, the dimension grows twice on each step. We begin with the dimension 1, so after n steps, we have the dimension equal to 2 to the n's. Can be seen that the previous algebra an minus 1 is embedded into our algebra an. So the new algebra is obtained from the previous algebra by adding a new element. We call it tilde E0, and its square is equal to the last parameter of doubling, gamma n minus 1. It is an easy example that the algebra an with the parameters gamma 0 and so on, gamma n minus 1, is isomorphic to the algebra an with the parameters signum gamma 0 and so on, signum gamma n minus 1. So since we consider real Cayley-Dickson algebras, we can only consider parameters equal to plus minus 1. If all the parameters are equal to minus 1, then we obtain the algebra of the main sequence. They are the most well-known, the most studied, and most authors restrict their attention to the algebras of the main sequence. We denote them by mn. Here m stands for main. And it's some of basic examples are the complex numbers, the quaternions, the octonions, and the less usual the sedenions. If the first n minus 1 parameters are equal to minus 1, it is the same, and the last one is equal to 1, then we obtain a Cayley-Dickson split algebra. We denote it by Hn, and here H stands for hyperbolic. Some examples are the split complex numbers, the split quaternions, the split octonions, and the split sedenions. The split complex numbers differ from the usual complex numbers by the fact that I squared is equal to plus 1, not to minus 1. So the only algebra A0 is just the field of real numbers over itself. The two algebras A1 are the complex numbers and the split complex numbers. We may assume that there are four algebras A2. However, there are only two of them up to isomorphism. And similarly, there are two algebras A3 S3 up to isomorphism. The main properties of these algebras are as follows. I will define alternativity and flexibility on the next slide. So we lose our properties, good properties, commutativity, associativity, alternativity on each step, but we do not lose flexibility. Okay, the associator of three elements A, B, C in A is defined by this formula. Clearly, the algebra is associative if and only if every associator is equal to 0. An algebra is called flexible if we have the following equality for all elements A, B in the algebra. And if the algebra is flexible, then we can linearize this equality and obtain that for all A, B, C, we have this equality. An algebra is called alternative if for all elements A, B, we have the following two identities. And it is well known that real Cayley-Dickson algebras are alternative if only if their dimension is at most 8, but all of them are flexible. There is a more accurate definition it was introduced by Morena for the case of real Cayley-Dickson algebras. We say that an element A alternates with B if only if this associator is equal to 0. However, since the algebra AN is flexible, it means also that minus the associator of BAA is equal to 0, so the associator of BAA is also equal to 0. An element is called alternative if it alternates with every element of the algebra. A alternates strongly with B if A alternates with B and B alternates with A. And A is strongly alternative if it alternates strongly with every element of the algebra. Now I will discuss relation graphs. Generally, relation graphs serve for the purpose of visualization of a binary algebraic relation R on an arbitrary algebraic structure S. And its relation graph is denoted by gamma sub R of S. Its vertices are either elements of the equivalence classes in S, and there is an edge from X to Y, if and only if X and Y satisfy our relation R. So the resulting graph is undirected if and only if R is symmetric. Relation graphs are usually defined on objects of some category, for example, on some Banach spaces or some algebras or a subclass of algebras, and they carry a lot of information. The most powerful thing that we can do is to solve the isomorphism problem. This can be done not in all cases, but sometimes it can be done. That is, we want to show that two objects of this category are isomorphic, if and only if their relation graphs are isomorphic. And this was already proved for some relation graphs, for example, for directed Birkhoff-James orthogonality graphs of smooth and reflexive Banach spaces with dimension at least 3, and for orthogonality graphs of finite dimensional formally real simple Jordan algebras. So the special cases of relation graphs are orthogonality and zero divisor graphs. Let A be an arbitrary algebra over a field F. We denote by Z of A the set of its zero divisors, and by ZLR of A the set of its two-sided zero divisors. Then the orthogonality graph gamma O of A is defined as follows. Its vertex set is a set of lines passing through 0 in the set of two-sided zero divisors of A, and two lines are connected if and only if they are distinct, so we prohibit loops, and their representatives are orthogonal, and by orthogonality we mean that both products of A and B are equal to 0. Clearly, this relation is symmetric, so this graph is undirected. We can also consider the directed zero-divisor graph. Its vertex set differs from the previous one in the sense that we consider all zero divisors, not only two-sided zero divisors, and there is an edge from A to B, if only if A and B are distinct, and AB equals 0. So these graphs are well defined, and we will often write just A instead of the line passing through A to avoid too long notation. In the case of real Cayley-Dickson algebras, there are some connections between these two graphs. For example, it can be proved that the set of zero divisors of AN coincides with a set of two-sided zero divisors. All zero divisors are two-sided, so we do not have to distinguish them. And if AB is an edge in a zero divisor graph, then the opposite to it is also an edge in the zero divisor graph. That is, AB is an edge in the Orthogonality graph. If only if one of the following condition holds. Either the line B is generated by the conjugate of A and the norm of A equals 0, or the traces of both A and B are equal to 0. So we wish to solve the isomorphism problem. We wish to show that two real Cayley-Dickson algebras are isomorphic if only if their orthogonality graphs are isomorphic. However, we know that real Cayley-Dickson algebras are alternative if and only if n is not greater than 3. So in the algebra A5 and in the higher dimensional algebras, we have zero divisors, which are very, very hard to study and to classify. So we cannot describe zero divisors, and moreover, we cannot describe the orthogonality graph. So what do we do to solve this problem? We consider good zero divisors. What are good zero divisors? These are zero divisors which satisfy some additional conditions on the norm and the alternativity of their components. So assume that AB alternates strongly with CD in the algebra AN, and the product of AB and CD equals 0 in the next algebra, AN plus 1. Assume also that the norms of C and D satisfy this additional condition for some real parameter chi. Here, the norms of C and D are just some real numbers. We have the following two equalities. Then we had one pair of zero divisors, and we obtain a new pair of zero divisors. Its first element is the second element of the previous one, and the second element is uniquely defined by our two elements. And here is chi. Indeed, we can just write the product of these two elements by the definition, and then we have to use alternativity 4 times. Here, 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 and here. And then the magic happens, and we have just these two expressions, which are in the formulation of our lemma. They're equal to 0, so the whole formula collapses, and we have just 0. Okay, but when does this condition on the norms of C and D hold? If the norms of C and D are equal to 0, both of them, then we can take any real chi. However, this is not the interesting case. We do not like it. We consider another case. Otherwise, the norms of C and D are equal up to multiplication plus minus 1, and chi is equal to this chi. Here, gamma n is equal to plus minus 1, so chi is also equal to plus minus 1. We call this condition asterisk, and we say that C and D satisfies condition asterisk with chi. This condition is satisfied automatically if our algebra AN plus 1 is either the algebra of the main sequence or is a Cayley-Dickson split algebra, since in this case, we immediately have the norm of C equal to the norm of D, but just with the restriction on the alternativity here. And So the values of chi equal to -1 and +1 respectively and are uniquely determined. However, this condition can fail in general, and there are some examples of it. I just omit them here in my talk. Why alternative elements are also good? Morena proved the following lemma. If x alternates with y in the algebra, then the norms of both their products are equal to the product of their norms. This equality is very similar to the definition of composition algebras. However, in composition algebras, this equality is satisfied for all elements, and in Cayley-Dickson algebras, it is satisfied rather rarely. For example, if x alternates with y. So let C and D satisfy condition asterisk, and the norm of either the norm of A or the norm of B is not equal to 0. Then, by using this lemma, we can easily obtain that AB and this new element, the conjugate of AC and minus chi dA, also satisfy condition asterisk with the same value of chi. Moreover, we can show that the elements AC and dA alternate strongly with the elements A, B, C, D. So why is this useful? We now return to our lemma. Okay, we had one pair of elements, and it satisfied the conditions of our lemma, and we obtained a new pair of elements. However, this new pair of elements also satisfies the conditions of this lemma, so we can use this lemma again. And then we obtain a new pair of zero divisors. We can then proceed and repeat this process 6 times. And after that, we obtain the following 6 cycle in the zero divisor graph of our algebra. We had AB connected to CD, then we obtained a new element. Then we have A minus B, a difference from AB only in the second component. Then C minus D. Then again, the element which differs only the second component from those one. And then again, AB, and we have a cycle. And this was in the case of arbitrary real Cayley-Dickson algebras. If our algebra is the algebra of the main sequence, then we have some additional properties which make the situation even better. So now our algebra is the algebra of the main sequence. Morena proved the following useful lemma. He showed that 2 elements x and y in the algebra of the main sequence satisfy xy equal to 0, if and only if yx is also equal to 0. So what follows from it? It follows that with any edge in the zero divisor graph, we have the opposite one to it. So the zero divisor graph can be obtained from the orthogonality graph just by replacing every undirected edge with a pair of directed edges. So we have this corollary. What else can we say about zero divisors in the algebras of the main sequence? Any zero divisors satisfies that the traces of its components are equal to 0. We call such an element doubly pure if it satisfies this condition. And if we had one product equal to 0, x and y equal to 0, and we define an element tilde y as y times tilde is 0, and it is equal to, we swap the components and take the first one with the minus sign, then the condition xy is equal to 0 is equivalent to the fact that x tilde y is equal to 0. So our corollary about the hexagons, in the case of the algebras of the main sequence, attains the following form. Let AB alternate strongly with CD, and the product of AB and CD be equal to 0. We do not need here the assumption that AB and CD satisfy condition asterisk, since it is an algebra of the main sequence and they satisfy it automatically with the chi equal to -1. Then there exists the following 6 cycle in the orthogonality graph. Here is no longer chi, and we can omit the conjugate because of the previous lemma, and all edges are undirected. Moreover, by using the last part of this lemma, we can extend this hexagon to the so-called double hexagon. The elements of the outer hexagon are just the elements of the hexagon, and the inner ones are tilde ones from the outer hexagon. So we have a, b, and b minus 1 minus a. The difference b minus 1 is minus tilde a, b, but this doesn't matter since we consider lines. And they are equivalent in the graph, that is, they have the same sets of neighbors. One can also consider this as 6 bipartite graphs k to 2. Here is graph k to 2 equal, and they are glued together. There are 6 of them, and they are all glued together. The double hexagon also satisfies a very convenient multiplication table of its vertices. We denote by f0 just e0 and by tilde f0 just tilde e0. The elements f1 to f6 are the elements of the outer hexagon. The elements tilde f1 to tilde f6 are the corresponding elements of the inner hexagon. And the last 6 elements are just auxiliary. They have one of their components equal to 0 and the other one equal to the product of components of some 0 divisors. And we then have the following multiplication table. It clearly has a block structure. There are 8 blocks with zeros in them. This actually means that the elements whose product is 0, they're a pair of 0 divisors. For example, f4 and f1 are a pair of 0 divisors. And there are 8 blocks which do not have zeros in them, and they resemble the multiplication table of the quaternions. However, they are not as isomorphic to it. There is no isomorphism that can turn them into the multiplication table of the quaternions. Okay, we now resume our task of solving the isomorphism problem. So what can we do? We have already understood that we cannot study the whole graph orthogonality graph of the algebra. So we study some good elements. And what are good elements? First of all, I would like to introduce the standard basis of a real Cayley-Dickson algebras. It is very well known. The standard basis of the 0 algebra is just the element e0 equal to 1. And then we construct the standard basis inductively. If n is at least 1, then the standard basis we denote it by en of the algebra an consists of the elements of this form. We either have a standard basis, a base element from the previous algebra as the first component and then 0, or we can swap them. So we have 2 to the nth standard basis elements. And one can verify that E0 is always the unit element of the algebra an. Recall also that we have tilde E0 defined as the pair 0 and E0, and we also denote En prime as a set of standard basis elements without E0, and En 2 primes is a set of En without E0 and tilde E0. And we also write tilde A equal to A times tilde E0 for all elements of the algebra. So standard basis elements are good in the sense that we understand them, in that sense that we mean. For example, any standard basis element is alternative, and the norm of every standard basis element is equal to plus minus 1. So all elements of this form, we call these elements pairs of basis elements, satisfy condition asterisk of some chi equal to plus minus 1. And we can apply corollary about the hexagons to orthogonal pairs of elements of this form, since all of their components are alternative. So they're good, and there is a finite number of them. So we can consider a finite subgraph on the set of these lines passing through these elements. More formally, we define the orthogonality graph gamma sub e of an plus 1 on pairs of basis elements as a subgraph of the orthogonality graph on the vertex set of lines passing through the elements of this form and their z pairs of basis elements, which are zero divisors, and the first component is not equal to E0. This means that the trace of this element is equal to 0. We need this condition to always pass to the second case in our proposition about the relation between zero divisor graphs and orthogonality graphs, since the first case is very narrow and this is not the interesting case, and we want the second case. Okay, so we proceed, these elements are very, very good, namely for any two elements, A, B, and C, D, which belong to this set of zero divisors. If their product A, B, C, D is equal to 0, then we know that the products of their components are either equal or minus, or one of them is equal to minus the other. So if A, B, and C, D belong to the same connected component of our graph, then A, B equals plus minus C, D. And moreover, these two elements are standard basis elements up to multiplication to plus minus 1. So for any element x, which is a standard basis element, we denote by C of x the subgraph of our graph on the set of vertices AB, such that AB equals plus minus x. We have shown that if x and y are distinct, then C of x and C of y are not connected to each other. And we can show that for any AB in C of x, we have the chi of AB equal to just gamma n times the norm of AB, and AB is equal to plus minus x, so it is equal to gamma n times the norm of x. And this value is the same for all elements of C of x. So we can define chi just on C of x by gamma n times the norm of x, and it is called the characteristic of C of x. We now give some low dimension examples. Moreover, we completely describe these graphs for dimension at most 16. So if n is equal to 0, then we have n plus 1 is either the complex numbers or the split complex numbers, and in both cases, we have an empty set of vertices. If n is equal to 1, then we either have an empty set of vertices. This case corresponds to the quaternions. Or the graph consists of two disconnected vertices, or it consists of 4 disconnected vertices, as here. 2 of them are in the C of E0, and 2 of them are in C of E1. And this is a graph of the split quaternions. Excuse me. If n is equal to 2, then either the graph has an empty set of vertices. This case corresponds to the quaternions. Or the graph consists of 2 hexagons, undirected hexagons, or it consists of 4 hexagons, as here. This is a graph of the split quaternions. Note that the first connected component, which corresponds to E0, is also a hexagon. We just pass here, 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 and here. So we have 4 hexagons. If n is equal to 3, then there are 4 cases instead of 3. We either have 7 double hexagons or 3 double hexagons and 4 bundles of hexagons. Do not worry, I will explain these words on the next slide. Or 4 double hexagons, 3 bundles of hexagons, and 1 almost complete 7-7 bipartite graph, or 7 bundles and 1 almost complete 7-7 bipartite graph. A double hexagon is as follows. We have already seen it. A bundle of hexagons differs by adding 2 new elements, and they are arranged in a new way. And an almost complete 7-7 bipartite graph is obtained from the complete 7-7 bipartite graph by removing the edges which connect the opposite vertices. So we do not have this edge, this edge, this edge, and so on. We can see that if the last parameter is equal to -1, then we obtain 7 connected components, and 7 is equal to 2 to the third minus 1. And if the last parameter is equal to 1, then we have 2 to the third connected components, that is 8 connected components. And this is not a coincidence. We will have the same relation in all the following graphs. Okay. So to sum up, we have for n equal to 1, 2 non-isomorphic algebras and 3 non-isomorphic graphs. For n equal to 2, 2 algebras and 3 graphs. And for n equal to 3, finally 4 algebras and 4 graphs. By the use of our complete classification, we can obtain the following corollary. If n, m, and m are between 1 and 3, and gamma and lambda are 2 sequences of parameters, and if also the graphs of 2 algebras have non-empty sets of vertices and are isomorphic, then the corresponding algebras are isomorphic. If n and m are equal to 3, then the curve also holds, and we have 4 algebras and 4 graphs. Their numbers coincide. Okay, but this is not true for n and m between 1 and 2, because there are more graphs than algebras. So there is no bijection between them. We now pass to the arbitrary case. So our main objective is to solve the isomorphism problem. And we have shown that this is impossible for n less than 3. So, and we have proved this for n equal to 3. So we are going to use induction on n at least 3. And we first learn how to construct our graph from the parameters of the algebra. We consider 4 types of connected components. So we just we don't know yet that C of x is a connected component, but it is almost almost always. And we consider 4 types of C of x depending on the type of x. In the first 2 types, x is equal either to E0 or to tilde E0, and the last 2 are as follows. Excuse me. So we will show that for n plus 3, these graphs C of x are exactly as connected components, except for possibly C of E0, which has an empty set of vertices if the last parameter is equal to -1. So on this slide, we provide an explicit form of the connected components of the first 2 types for various values of the last 2 parameters. C of E0 depends on the last parameter only. If it is equal to 1, then we have the following graph. It is an almost complete bipartite graph. And if gamma n is equal to -1, then we have just an empty set of vertices. And C of tilde E0 depends on the value of the product of the last 2 components, 2 parameters, and it can be described as follows. What do we want from these graphs? One can verify that if n is at least 3, then all these graphs are connected, and the diameters are equal to 3. We now construct the remaining components by induction on n. We denote by an with a circle the algebra an. It has dimension twice less than our algebra n plus 1. Its first n-1 parameters are the same as in an plus 1, and the last one is just the last parameter of our algebra. And an with a bullet differs from an with a circle by the last parameter. It is equal to the product of the last 2 parameters. So we are going to reduce the orthogonality condition in our algebra an plus 1 to the orthogonality conditions in these two algebras. So let A, B, C, D be pure linearly independent basis elements in A n minus 1. And we consider first the connected components of the third type. Let X and Y belong to the sets. Then X and Y are orthogonal in our new algebra, if and only if A, B, and C, D are orthogonal in A n with a circle. So we reduced our orthogonality condition to the previous algebra. And we denote this condition by a dashed edge in our next slide. In the case of the connected component of the fourth type, if X and Y belong to the sets, then X and Y are orthogonal in A n plus 1, if and only if A, B, and C, D are orthogonal in A n with a bullet. And we denote this by a dotted edge. So connected components of type 3 look at, as follows. They depend on the value of chi. On the left, there is chi equal to -1, and on the right, we have chi equal to 1. If chi is equal to -1, then we have 4 elements which we call special. Why is it special? They play the role of hubs, since every other element is connected to exactly one pair of them. CAB is connected to the left pair of special elements, and tilde A, tilde B is connected to the right pair of special elements. So the diameter of this graph can be shown to be equal to 3, since we take, for example, AB, then move to the nearest special element, say tilde X tilde is 0, and then go from construct a path from this element to some other elements, for example, to tilde C minus tilde D. And there is always such path. So the diameter of the graph is equal to 3. And if chi is equal to 1, then we have 2 extra elements. They have their last components equal to E0 or to minus E0. And they're special now. And the previous 4 elements which were special on the left side are not special now. They're here. And the diameter of this graph is again 3. And there are dashed edges. Say C minus D is connected to B minus gamma NA by a dashed edge. So there is an edge if and only if A, B, and C, D are orthogonal in A n with a circle. The connected components of type 4 are very, very similar. So we have the same 2 cases. They just differ by the labels on the vertices. They're a bit different. And we have dotted edges instead of dashed edges. So we now reduce the orthogonality conditions to A n with a bullet. Okay. So we have shown that if n is at least 3, then C of x is connected for any basis element x, and its diameter is equal to 3, except for possibly C of E0, which can have an empty set of vertices if gamma n is equal to -1. So these graphs C of x are exactly the connected components of our graph. So we have the following proposition. If n is at least 3, then our orthogonality graph has either 2 to the n's or 2 to the n's -1 connected components, depending on the value of the last parameter. The number of the vertices in a connected component is given by this formula, which depends only on n and the value of the characteristic of C. So we can see that the first case, there are 2 elements more than the second. So this proposition doesn't contradict to the explicit form of the graphs of 16-dimensional algebras, and it should be so. So this is not surprising. what do we do now? We had an algebra and we constructed its graph. We now want to solve the reverse problem. We have a graph of an unknown algebra and without labels on the vertices of our graph, and we want to determine the parameters of our algebra up to isomorphism. We have proved that we can do this for n equal to 3 in our corollary. So we are going to use induction on n. We have the following proposition. Its first part follows for the previous proposition. It is very straightforward. If n is at least 3, then we can determine n, the last parameter, and if the last parameter is equal to 1, then we can find C of 0 because we just know how it looks. Moreover, we can find the characteristic of each connected component C. If n is at least 4, then we can also find C of tilde is 0, and so we can determine the previous parameter, gamma n minus 1. But this is not as trivial as the previous part, the first part. However, we can do this. So we have found C of 0 and excuse me. Okay. And C of tilde is 0. So we now have the remaining part of our graph when n is at least 4. So we have just the connecting components of the third and the fourth types. And we wish to obtain the previous graph. But which graph is previous? There are two previous graphs. They correspond to algebras AN with the circle and with the bullet. We already know the last parameters of these two algebras, so we have the connected components which correspond to E0. Consider an element X, which is a pure basis element in the algebra A and minus 1. Then the connected components, component C of X should be reduced to the connected component of the graph of AN with a circle, and C of tilde X should be reduced to the connected component of the graph of AN with a bullet. If C of X is transformed, then chi is preserved, and if C of tilde X is transformed, then chi changes sign. So on the next slide, we show the process of reduction. We call it reduction. And the bold lines denote those edges and vertices which are preserved. See here, these elements and the edges between them are preserved, and all others are deleted. And this is the case of the connected component of the third type with chi equal to minus 1. And if chi is equal to 1, then we preserve these vertices and these edges. Okay, and if we consider the connected components of the fourth type, then since now the value of chi changes sign, we also need to change, to swap our sides, the left and right. So note that we swapped them, kind of. So now if chi is equal to minus 1, then we preserve these edges, and if chi is equal to 1, then we preserve these edges. However, this is not the end of the algorithm, since we use here we know here which elements are special. We use this, and we also have to know which connected components are of the third type and which are of the fourth. However, we can do this, namely by this algorithm, but this is too long to present in this talk. Okay, so we can now construct the previous graph, and we now ready to prove our main theorem. We will use essentially the following lemma by Akin and Sazaya. They showed that if n is at least 3 and gamma and lambda are two sequences of parameters, then the algebras of the same dimension to the n plus 1, and which correspond to gamma and lambda are isomorphic, if only if the last parameters are equal, and the previous algebras are isomorphic. I should note that they proved this lemma for the case of an arbitrary field, and I just used the field of real numbers. In the arbitrary field, this condition takes the form that the inverse of gamma n times lambda n should be a square of some non-zero element of a field. And in the real case, since we consider only parameters equal to plus minus 1, we have this equality. Okay, so our main theorem is as follows. Let n and m be at least 3, gamma and lambda be 2 sequences of parameters, and then the algebras which correspond to these parameters are isomorphic if and only if their graphs are isomorphic. How do we prove this? We immediately obtain n equal to m on both sides. Here we have it from the dimension, and here we have it from the proposition that we had. And then we prove the theorem by induction on n, just by our two processes. We can construct the graph by the parameters of the algebra inductively, and we can find the parameters of the algebra by its graph. Okay. So what happens if n and m are less than 3? If the graphs have non-empty sets of vertices, then the implication from right to left holds for all values of n and m. However, the implication from left to right may fail for n and m less than 3, and we have shown that before. Okay. So some open questions. We have studied elements which satisfy some additional conditions on the normal alternativity. But what happens if we preserve the conditions on alternativity but do not require the condition asterisk? So what happens if an element AB is doubly alternative, so both of its components are alternative in the previous algebra, but this condition fails? What other important properties do the double alternative elements with condition asterisk possess? Now we have explicit formula for their annihilators, centralizers, orthogonalizers, and we know that these elements are very good. However, what can we say about them also? In real Cayley-Dickson algebras, orthogonality and commutativity as relations differ by one linear equation. So it is clear that these two relations should be very closely related, and thus their graphs should be related. So how? What is this relation? We know that for the case of the sedenions, it is not as simple as we can imagine, and the graph becomes rather complicated, the commutativity graph. But the orthogonality graph is very well studied. And it is also interesting to see under which conditions are two elements of a real Cayley-Dickson algebras or equivalent or C-equivalent. That is, have the same orthogonalizer or centralizer. So here are some references. My talk was based on the works on the 3rd, 6th, and 7th papers. I would also like to mention the works by Biesdager, Isaksen, and by Morena. They studied zero divisors in the algebras of the main sequence, and many of their methods can be transferred to the arbitrary case. And I also use this paper by Eiken and Cesare, namely their last lemma. In their work, it is a corollary. Okay, thank you for your attention. Do you have any questions?
Many thanks, Svetlana. Any questions or comments, please?
Okay, I assume that there are no questions. So can I stop the demonstration?
Yes, thank you very much.
Thank you.